Today I'll be presenting my work, which here the kind of overall idea, the title of the presentation being graph-based reasoning for dialogue models. So let's see. Okay, now it's working. So to start with, what are dialogue systems? Is a very basic starting point here. So dialogue systems are an autonomous system that can interact with a human through natural language, and this is either written or spoken. And these have become kind of a more prominent topic in NLP over time as the capabilities of various NLP models have improved. And so this idea of a system, a computer or a robot even speaking with people is kind of one of those exciting ideas that's kind of puts a lot of aspects of various research in NLP together. And so these can either be open domain, which is to say a bot that can talk to anybody about or talk about any topic with a person just for the purpose of conversation itself, or they can be task-oriented, which is a more specific type of system which is going to try to accomplish a given task, like Amazon's Alexa looking up the weather or various information from the internet. And a fundamental aspect of any dialogue system is this idea of turn taking. So it's the just simple flow of the user speaks or writes to the system, user utterance, and receives a reply. And the conversation with the system goes on like this in this turn-taking fashion until the dialogue is completed. And dialogue systems are frequently underlied by a large language model component, and this is also something that's become of increasing interest, and especially in recent months with ChatGPT making quite a big impact and got a lot of attention and the media for very good reason. These models have become really impressive over time in their ability to speak and converse naturally with users, and just provide this kind of natural language response that's very convincing and very able to interact with people well. But despite the fact that these models have really impressive capabilities, there are still limitations and there are still challenges that haven't been solved. And one of them is that their ability to reason can be limited in some contexts, especially when posing, say, a logic problem. So in some recent work, other research groups have demonstrated that there are limitations, particularly when irrelevant information is introduced to the context. So off to the right, you have a logic problem that says, okay, how old is somebody given these facts? But if you modify the problem and just add other things, then the model is very apt to get the question wrong or to get the answer wrong. And there are various instances of this involving reasoning upon the information that it's been given. Sometimes it's able to figure it out, but many cases it's not, especially when it's a very novel problem. So this overall idea is that reasoning and actually using, well, what we would call reasoning is something of a challenge for language models. So the question in my research that I've been working on and continue to work on is if we can reduce the amount of irrelevant background information in a context and at the same time improve the information available with common sense reasoning, can we improve the system responses? So this approach, or this kind of investigating this question, leads us to combine three elements here. The first is to represent the information that's relevant for the dialogue, or all information of the dialogue as a graph, a single unified graph that represents the information of the dialogue. And of course, I'll get more to that later. Extending the information available to this to the dialogue system. So this information represented as a graph, we can extend it with logical reasoning on that graph. And then the third element is to take this graph and verbalize that information and turn it into a natural language medium so that a language model can take advantage of it, since the input of a language model is language. So starting with this approach, we have to ask ourselves, what should the system reason about? And so coming back to this notion of open domain and task-oriented dialogue systems, in an open domain, this could be anything. So this is kind of a very large problem, but when we look at task-oriented dialogue, and this is the area that my work is focused on, we have a somewhat narrower picture, and this kind of makes it a little bit easier in a way to say, okay, we have bounds on what we're going to expect the system to reason about. We have a more defined picture of that information. So, for instance, if the dialogue agent is a receptionist, then we would expect that it's going to know about the people and places in the office it's the receptionist for, or events on a calendar. So if you come up and you say, I need to know where so-and-so's office is, then the receptionist should be able to point you to where that person's office is. And it is also useful if we can take information about what's been said in the dialogue. So not just the people and places of the location, but what's been discussed. If a person says, oh, I'm looking for somebody, but that person doesn't exist, it may still be useful to be able to reference this person, even though they're not working at this office. Maybe it's relevant in some other way that you might want to refer back to. So various other things that come out of the dialogue in terms of the utterances and words themselves can be useful as well. So that leads us to representing this as a graph. And so graphs are very frequently used in dialogue systems in a lot of ways, because graphs are is a very large topic in itself as to what one can do with graphs, what kinds of graphs exist. But for our purposes, the main point is that we want to use a dynamic knowledge graph. And so it's dynamic in the sense that as the dialogue progresses, we want to add nodes, add information to it. So as mentioned before, as the user speaks and gives utterances, and as the system replies, those utterances and that turn taking is added as elements of the graph, along with the background information that we want to reason about, like places or people. And it's a knowledge graph in the sense that it represents semantic knowledge about the world, semantic relations. So in the diagram off to the right, you can see that the corridor is connected to the kitchen. So this is a kind of semantic triple that tells us, okay, these two locations have a relation to each other, or Oliver is an employee at a company. And again, that's kind of the fundamental building block that we're going to reason on. So a first pass at how we might kind of construct that or add that dynamism to the graph is to say, okay, we start with first a human utterance. At the beginning of any dialogue, we're going to have the human speaking to the system, and they're probably going to want, they're going to have an intent. So here saying, where is John, is just the starting point. And from that, we can infer that they're looking for a person. And so that's the intent, that they're requesting person's location. And this John is kind of an entity mention. Now, we don't know if John exists in the graph or not, but we do know that it exists in the utterance. So we can start by saying, okay, this is what we should look for. We can identify that part of the utterance as something potentially an entity. And then looking into the graph of the background information, we can link that to, say, John Doe here is saying, okay, we have a person in the graph named John. So if we can create that link, then we can subsequently create new nodes to represent, okay, this is how the system should respond. So this is kind of the flow from the utterance to the agent response, is first linking relevant information from the utterance into the graph, and then subsequently modifying or adding nodes that might be relevant to the response. But this was, of course, an initial model, and so things like user intents or the ASR hypothesis, so using different alternatives for what the user might have said. While in theory that could be useful, that's not something that we're presently doing. So we focused on entity mentions and entity linking. So entity linking is is this process of taking the entity mention from the utterance, so that can link to a person, a place, or any other object in the graph, and creating an edge from that node that represents the entity mention to a node in the graph, which is the concrete known entity. So in the diagram graph to the right, the blue dotted arrow represents this, the creation of this edge. So given an utterance that says what events are taking place in alpha, we identify first that alpha refers to a place, that it's the name of a meeting room. And then, based on heuristics like string similarity or references further back in the graph, we can say, oh, this is a reference to the alpha conference room. So then that semantic relationship of the user mentioned a place called alpha, and that mention refers to the alpha conference room. Then we have this kind of intuition of what the user is talking about. So once we have that, then we know a little bit more. We have an indication of what we want to reason about. And in order to do this, we can define rules. So rules, now, of course, rule-based systems are kind of an entire topic in themselves as well. But the important part is that using any kind of logic engine, in our case, we used something called Problog, which is a probabilistic extension of the logic programming language Prolog. But the core idea is that this is a system, a set of rules that can be evaluated on the graph. So an example of this is if we have a person in the graph, we have an event in the graph, and we know that the person is an attendee of the event, and the time of the event is t, then we can infer that the person is probably busy at that time. They're not going to be available for a meeting. And that's the kind of common sense reasoning that might be difficult for a language model, is to say, okay, it may know that the person is at a meeting, and it may know that the person is at the meeting is at a given time, but it might not necessarily explicitly know that the person doesn't want to or wouldn't be able to schedule a meeting at that time. So a large or small, however many, set of rules can define the conditions under which a person is busy, or any other semantics that we might want to express or make explicit to the dialogue system. So having come up with these, the facts that point us in the direction of what important attributes or what is important about the state of the world, we can add them to the set of facts derived from the dialogue state graph. So after we take the graph and convert it to a set of facts, then we're adding the facts that are derived from the logical rules to that set of facts. So here, that busy, the fact that Jill Martinez is busy at 1 o'clock becomes a fact, just like any of the other facts in the graph. Once we've done that, then we take these relations, these semantic triples, and we can sort them into templates. And these templates are linked to the relation. So if a person is organizing an event, we can express that with a natural language template. Person is organizing event. And the particular values of the person and the event can just be filled in based on the value that's stored in the graph. And this verbalization process allows us to construct a document of sentences or sentences describing all of the semantics of the graph. So why is this useful? Why do we want to do this? The purpose or the usefulness of a document like this is for a technique called retrieval augmented generation. And retrieval augmented generation is essentially adding that document or adding some kind of prompt in addition to the other input you have for the language model in order to improve the response. So this process works like this. We have two parts. The first part is the graph description, as before, and the second part is the dialogue context. And these two are essentially, they're concatenated and given as the full context to the language model. So the language model has access to both of these aspects at once. Then the goal is for the language model to be able to identify relevant information. So in this context, the person in their last utterance is asking for the room number for Mark Suarez's office. And here in the context, we can see that it's room 270. So the system should be able to respond like as follows and say his office is room 270. And then the conversation continues from there. So each turn in the dialogue is essentially represented like this, consisting of both the dialogue context and the graph description. But as much as this helps, and even though we have the dialogue state information in a form that a language model can use, there's still quite a bit of information. And especially with a large graph, this document and the set of information grows to a very large degree and is very likely to exceed context windows in language models, which inherently have limitations on how much you can actually feed to them. So between the dialogue context and the dialogue state information, there might just be too much to be able to feed into the language model. But at the same time, we do want to keep as much information as we can. We want to keep relevant facts that are going to help the system to be able to accomplish its tasks. So we have to strike a balance here. We want to keep the relevant information while avoiding the irrelevant information that might confuse the system when it's trying to process the user's request. And a further challenge to this is that we don't really have any labels on the dialogues. We don't have any labeled data that says this fact is relevant for this turn of the dialogue. So how do we solve that? So with our approach, we used a relevance model. So this is, in essence, a simple feed-forward neural network, which is able to select facts and is jointly trained with a language model on the dialogue data. And so the way this works is that given a dialogue history and a response, we can take a look at the facts that we have available and the facts that underlie that dialogue. And we can test and see, does each fact help or hurt the language model, training a language model in generating a response. So off to the right, for example, we have the set of facts relating to Jill Martinez. It's only really necessary to know that we have a person whose name is Jill Martinez and that she's busy at 1. The other facts are not really relevant. We don't need to know the name of the status update that she's attending, and we don't even necessarily need to know that we're talking about today, as long as these facts are sufficient for the answer. But this is something that's data driven. We don't want to just say, well, we can think that this might be relevant or that might be relevant. We can just let the data decide here. And in this way, so we're jointly training it without labeled data. So in order to accomplish this, and for our experiments, we used 2 data sets, one called GraphWaz and one called KVRET. And GraphWaz was a data set that we collected earlier in my work, which is essentially a reception-based dialogue where the receptionist is discussing, or a user talks to the receptionist to accomplish a task, to ask about people's offices or scheduling events. So each dialogue contains a fictitious organization structured as a graph. And then the KVRET dataset is a slightly different dataset, but it also has this notion of each dialogue having an associated knowledge graph. But it's in 3 domains: weather, navigation, and calendar scheduling. So these are, and particularly the calendar scheduling is quite a bit similar to GraphWaz. But yeah, in both cases, we're looking at, there's a set of relevant information as a knowledge base structure, or a structured knowledge base underlying each dialogue. So the experiments we conducted for this, we wanted to test 3 things. The first was a model which used only the dialogue history and had no access to the background knowledge. So this is our base case, essentially. This is what can a dialogue system do, or how will it respond, given that it has no ability to access the knowledge or the facts underlying the conversation. The second model is a model which uses all the facts, including facts derived by logical rules. So this is giving everything at once with no filtering. And then the third model is a language model which is able to use relevance, facts selected by the relevance model. And then we can try this with and without the logical rules to see how well that works. And we evaluated this with two LLM models, one called Godel and one called GPT-3, or one, the very famous GPT 3.5. So then another aspect of this evaluation is that we want to look at, or we want to know what types of errors we might expect the dialogue system to make. So we're trying to cut down on, firstly, hallucinations, which is a famous problem with LLMs. And so how we define them here is that they're statements of facts that directly contradict the knowledge base. So anything that refers to a non-existent entity or is saying, sure, I'll schedule a meeting at a time when that person was busy. If the system is, maybe you could think of it as the system is actively lying to the user in a sense by actively providing inaccurate information or actively taking an action which causes a problem. And then the second class of error is more of a negative type of error. It's a retrieval error, as we call it. And this is a statement where the system kind of waffles or says, I don't have access to that information, or I'm not sure, when in fact you would expect that the receptionist would be able to. If you say, where is Mark Suarez's office? If the receptionist says, oh, I don't know, that's not really helpful. It's not really accomplishing the task that it's supposed to accomplish. So these are the two types of errors that we want to look at. So when we evaluate the performance of these models, when we looked at the first thing we looked at were automated metrics, and Blue, Meteor, BERT score. These are just notions of how fluent the result is, or how well it matches to the gold standard response in the data set. And so the results here didn't differ significantly. There were slight increases in the Blue score when we used the relevance scoring model with the logical facts, but it wasn't a substantial effect. So this wasn't necessarily indicating that there was a huge improvement in the fluidity or the ability of the system to respond exactly how the gold standard was in the data. But that's not necessarily the core part of it, or the most important aspect of it. But it would have been nice to see. But we then evaluated the more important aspect of it, the hallucinations and retrieval errors. And this was using GPT 3.5 with the GraphLaws dataset. So here we see that the number of hallucinations did in fact decrease when we used the relevance scoring model. And especially in the dev set, the logic, the relevance model, which included logic-derived facts, decreased the hallucinations quite a bit. Now, it was about equal in the test set, but the overall amount of errors was quite a bit less. So the retrieval errors also went down. So if you look at the overall trend, there is a balance between the retrieval errors and hallucinations. But overall, the addition of the relevance scoring model with the logic did decrease the overall number of errors. And then to follow this up, we also experimented with human participants. So this way we would have a fresh data set, a fresh in the wild experiment with people talking to the dialogue system to accomplish tasks in a very similar manner to the GraphLaws data. So they were given a task, which gave them an alias and a general idea of what they wanted to accomplish. So to schedule a meeting or to find out who was attending a meeting, or various things that they might ask a receptionist. And they were given latitude to complete the task as creatively as they saw fit, so that the dialogue could be as natural as possible. So for each dialogue, the model that the user was interacting with was randomly selected so that they didn't know which one was which. And So then we did the same kind of an error analysis. We evaluated the proportion of terms containing hallucinations and retrieval errors. And again, we observed that the addition of the relevance model and logic reduced the overall number of errors. And specifically, within each model class, we saw an improvement in the error rate. The interesting thing here, well, one thing to note is that in the Gödel model, the number of hallucinations was technically the lowest, with the model which used no facts whatsoever, but the retrieval errors were very high, which is just indicating that it said, I don't know, a whole lot of times, in essence. But then with the GPT model, the trend was somewhat the opposite, that the hallucinations were highest in the no facts model. So that kind of indicated that the model had some propensity to just go with the flow and say, yeah, sure, I can schedule a meeting with a person who doesn't exist. And that's kind of the well-known problem with GPT models, is that they're sometimes too accommodating in that regard, that they'll kind of fake it till they make it at times. So yes, so that's the overall conclusion here, was that this does seem to reduce the number of errors that we observe. And we also asked the users to score the dialogues. So at the end of each dialogue, we asked them to score on a scale of 1 to 5 how well that dialogue system did, or how well that dialogue itself went. And the first was to say whether it responded to them in a relevant way. And the second question was whether they got the task done. And this, again, slightly relates to the two error notions that we had before, but not exactly. And so, again, we observed that the scores were highest, generally speaking. Well, with the Gödel model, the scores were clearly the highest with the model using the logic enhanced facts and the relevance model. The results were slightly more equivocal with the GPT models, but the task score was the highest with the model which used logic. Slightly lower appropriateness score. And funny enough, the highest appropriateness score was from the no facts model. But overall, this seems to indicate that there is some benefit to using logic derived facts in this way, and providing this kind of background filtering for the model. So so this is the continuing and ongoing work, of course. There's more that we want to test with this to see if we can improve upon this idea, see if using other rules or other types of data, particularly visual data or spatial data, such as if we keep track of a robot in physical space. So the previous experiment was conducted with dialogue systems through the medium of text, but it might be a far more interesting problem to do this with a robot. So we're currently working with a Pepper robot, which was visualized on some of the earlier slides. So the current work is to integrate spatial and visual data in addition to these other types in order to have a more multimodal approach and investigate these kinds of this approach to using logic-derived rules and reasoning with the graphs. So yeah, that is the idea, and yeah, thank you very much.